Welcome folks, a video on a main technique of integration called substitution. Um, in this video, we'll see how the strategy of substitution can be used to undo the chain rule, among other things, in order to evaluate indefinite and definite integrals. A quick reminder about the difference between indefinite and definite integrals. We saw last time how the definite integral is related to the antiderivative. Accordingly, we use the indefinite integral, therefore, to define or rewrite the antiderivative of a function. So when capital F is any antiderivative of little f, we can express that with an indefinite integral as the indefinite integral of little f of x dx is capital F of x plus c. Accordingly, we have all sorts of rules for antiderivatives that we can use now in these indefinite integrals. Power rule. We can use the rules for antiderivatives for sine and cosine and so on and so forth to evaluate antiderivatives. Okay, so motivating problem. Here's a motivating problem. We know how to find the derivative of this function, 1 plus x squared. There's just some chain rule involved here, and I won't go through that. But the chain rule tells us that the derivative here is x over the square root of 1 plus x squared. So we can write this using our new indefinite integral notation. So here's that same derivative rule using an indefinite integral notation. Now, of course, the integrand here doesn't seem to follow any of our rules for antiderivatives. So it's hard to see how you would get from one to the other without actually knowing the derivative in the first place. And that's the goal of the substitution rule. So if you want to think about this in a different way, you can think about this in terms of derivatives of compositions of functions. So more generally, when the derivative of a composition f of g of x is f prime of g of x times g prime of x, of course, that's the derivative of the outside function evaluated at the inside times the derivative of the inside function, we can write that the antiderivative, or the indefinite integral of f prime of g of x times g prime of x is f of x plus c. And that's sort of what we're going to be doing here, is thinking about looking at a function in terms of a composition. Okay, so more generally, the substitution rule here, just in terms of f and g primes, is the following, that and there's a slight typo on this page, so let me go ahead and fix that. There's a typo. The left-hand side should be above, should be f of g of x times g prime of x, and we'll express that as f of u du. So the general strategy here is that in order to simplify a complicated integrand, you should sort of be looking for a function and its integral, or its derivative, and then set that function equal to u. So we'll try the substitution u equals g of x, and of course from Calc 1 we know that du is g prime of x dx, and this allows us to simplify the integrand in terms of u, a new variable that we've substituted for, instead of x. So in general, we'll rewrite the complicated integrand in u world as the indefinite integral of f of u du. Hopefully that's something that we can deal with our rules. So a few examples to illustrate this idea. The first one is substitution to evaluate the indefinite integral of the quantity x squared plus 1 to the 10th power times 2x dx. So following what we did last time, here we'll set u to be the inside function, x squared plus 1. So when we try u equals x squared plus 1, of course, du is 2x dx. And we can then go ahead and evaluate the resulting indefinite integral in u world. So substituting into u world, we can see that we're left with the integral of u to the 10th du. Of course, we can just use the power rule for integrations to rewrite this as u to the 11th over 11. Of course, what we're really interested in here is an indefinite integral in terms of x. So substituting back what u was here in terms of x, we see that the indefinite integral is 1/11 times the quantity x squared plus 1 to the 11th plus a constant. Second integral, substitution to evaluate the indefinite integral sine of 3x dx. Sort of using the same strategy as last time, we'll go ahead and let u be 3x. Now I'm going to walk through this example a little bit differently when u is 3x, du is 3 dx, or we can write dx as 1/3 du. So we'll go ahead and rewrite the indefinite integral here in u world using those two substitutions. So manipulating the integrand to substitute u equals 3x and dx equals 1/3 du, we see that we're left with indefinite integral of 3 sine u times 1/3 du. Of course, we can manipulate the integrand, pulling those constants out front. They eventually cancel out. And when that happens, we're left with the integral of just sine of u du. Of course, the derivative that you take of the function you take to get back sine is negative cosine, and we'd like this to be in x world instead. So we express the indefinite integral here as negative cosine of 3x plus some arbitrary constant. Okay, one more example showing the substitution with a different manipulation of the integrand. Using the same hammer that we used last time to bang in this nail, we'll go ahead and try u equal to 4x. Manipulate the integrand, and then evaluate the indefinite integral. Okay, in this case, we substitute u equals 4x. We substitute du equals 4 dx, or dx equals 1/4 du. And in doing so, we have a new integral, indefinite integral cosine u times 1/4 du. We can pull the 1/4 out in front of the indefinite integral. And of course, the function that you take the derivative of with respect to u to get back cosine of u is sine of u. That's the antiderivative. So in x world, we find that the antiderivative of cosine 4x dx is 1/4 sine 4x plus an arbitrary constant. Now it's worth mentioning that since we're experts in taking derivatives, we can always check our answer by thinking about the indefinite integral as it relates to the antiderivative, right? So what we're saying here with this indefinite integral is that an antiderivative of cosine 4x is 1/4 sine 4x. And to check, just take the derivative. And if you think it out, it's pretty straightforward. The derivative of 1/4 sine 4x is 1/4 times cosine 4x times the derivative of the inside function. Of course, the derivative of the inside function here is just 4, which cancels out the 1/4 out front, and you're left with cosine of 4x again. So in all of these indefinite integral problems, you should always be able to check just by going back to your understanding of the derivative. Okay, the same idea works with definite integrals too. And the key to this thought process is that in the definite integral from a to b f of x dx, the a and the b represent values of x. So in order to think about the indefinite integral in terms of a substitution, what we do is substitute the limits also. So I often refer to the substitution as moving to u world, and our general strategy here is going to be to move the limits to u world as well. So the substitution rule in terms of a complicated integral here for a definite integral will set u to be g of x, and then the new wrinkle here is that these limits are also substituted according to that same rule into u world. So our limits a and b become g of a and g of b under this substitution, u equals g of x. So a couple examples to illustrate that. Here's the first one. Let's go ahead and use the substitution to evaluate this definite integral 0 to 1 x times the quantity x squared plus 1 to the 10th power dx. Now this integral is a little bit like the one we saw before, a little bit different, but we'll go ahead and use the same substitution as before, which is u equals x squared plus 1. From that substitution, like we did before, we'll compute du and then substitute the integrand and the limits all into u world. So here's the entirety of our substitution, u equals x squared plus 1. We can manipulate the integrand however we like. I'll go ahead and use dx equals 1 over 2x du. And when x is 0, u is 1. When x is 1, u is 2. And again, those relationships come exactly from the substitution that we created here, u equals x squared plus 1. So rewriting the integrand in u world, we see that it's now quick to evaluate just using the fundamental theorem of calculus. So again, here we've substituted u equals x squared plus 1, dx equals 1 over 2x du. We're still left with a couple x's in the integrand, which is problematic in general, but in this case, those x's cancel, and we're left with an integral that is entirely in terms of u that we can evaluate using the fundamental theorem of calculus. Now, before I go on, I want to point out that I've also substituted these limits into u world from our computation above, right? So those are the correct limits in u world, and I forgot to reset my screen. Sorry about that. Okay, so now we can evaluate this integral in terms of u. Simplifies nicely. So the number we get here is kind of a nasty number. At the end of the day, we end up with 1/2 times u to the 11th over 11 evaluated between 1 and 2. So we get 1/22 times 2 to the 11th minus 1, which is a number. And that's what we expect for the value of the definite integral, is to get a number. Okay, one more example illustrating an integral by substitution. We'll use substitution to evaluate this definite integral cosine of 3x dx. We've sort of seen the integrand here before also, so we'll go ahead and use u equals 3x, substitute the integrand and the limits, and then evaluate the new integral in u world. So here are the details behind that substitution that transfers this integral involving a composition to an integral just involving the plain variable u into u world. So integral 0 to 12 pi over 12 of cosine 3x dx is the integral from 0 to pi over 4. Of course, we have a factor of 1/3 from the substitution, cosine of u du. This integral we can evaluate quickly using the fundamental theorem of calculus. So of course, an antiderivative of cosine of u is sine of u. We'll evaluate that between 0 and pi over 4. Sine of pi over 4 is 1 over root 2, and everyone knows that sine of 0 is 0, so we end up with the value 1 over 3 root 2 for the indefinite integral. Okay, a couple other miscellaneous facts here. Using substitution to evaluate an integral involving a composition is most common, but sometimes a substitution method isn't quite as obvious. So we can illustrate that fact using substitution to evaluate this indefinite integral. U equals 2 times a quantity, or x times a quantity, square root 2 minus x dx. So in this case, sort of the annoying part of the integrand is the square root. So we'll go ahead and try the substitution u equals 2 minus x and just see what happens. So here's our first attempt at substitution to simplify the integral, and you can see that we've substituted the quantity 2 minus x, replace that by u, replace the quantity dx with minus du, but we're not quite finished yet because our integrand isn't completely in u world. So common mistake that calculus students make is failing to take the integral all the way to u world. This is problematic. Here we can see that we can take the integral all the way to u world just with a little bit of help of our original substitution. So that original substitution was u equals 2 minus x. We can manipulate that relationship to solve for x equals 2 minus u and substitute that quantity in for x. I've done a couple other things here, expressed the square root of u as u to the 1/2 and then pulled the minus sign out front of the indefinite integral. And once you do that, it's pretty quick to manipulate the integrand, evaluate using power rule for antiderivatives, and then just rewrite the antiderivative in terms of x world, the original variable. So here's that manipulation. Minus out front, indefinite integral of 2 times u to the 1/2 minus u to the 3/2. Power rule for antiderivatives on both of those functions. Simplify, simplify, simplify. And finally, substitute the original variable u equals 2 minus x to find the antiderivative. Okay, one more comment about definite integrals and symmetry. A function is called even if f of minus x equals f of x. And one property of even functions is that the definite integral of an even function on a symmetric interval is twice the definite integral of the even function just from 0 to a. You can prove this using substitution. I challenge you to do that. In this case, just use the substitution u equals minus x and divide the integral up into two parts. Okay, so again, this makes use of the pit stop property. We'll integrate from minus a to 0 and then from 0 to a, divide the integral up into two parts, and then use the substitution u equals minus x on 1. This makes sense intuitively. The area under the curve of such an even function on the entire interval from minus a to a should be twice the area from 0 to a. Similarly, when f is an odd function, the integral of an odd function on a symmetric interval is 0. And just keep in mind that when f goes below the x-axis, the definite integral represents the net signed area. Of course, when f is odd or symmetric about the origin, the graph is symmetric about the origin, the net signed area should be 0. And you prove this in the same way using the pit stop property to divide the integral up into 2 bits, and then using the substitution u equals minus x on one of those bits. Okay, folks, hope you've enjoyed this video on the substitution rule. Have a great day, and we'll see you next time. Bye-bye.